Yeah.
Thank you very much for the introduction. Did you see the presentation?
Yes, we can see.
Okay. Okay, so thank you for this opportunity to have me at this conference. My name is Maciej, and as was said, the topic of my presentation will be nanostructured silicon aluminum oxycarbide glasses-based coatings for solid oxide fuel cells interconnects. And in the beginning, I would like to tell just a few words about the problem of high temperature corrosion of interconnects in solid oxide fuel cells and my solution in terms of protective conducting coatings based on polymer derived ceramics from silicon aluminum oxycarbide system. And then I will show some studies concerning both isothermal and cycling oxidation oxidation in such conditions. So let's start with solid oxide fuel cells. And what's all about these fuel cells? It is an electrochemical device which allows to produce heat and electricity on the way of electrochemical redox reactions. And from all of the fuel cells, the solid oxide fuel cells stand out with the highest power efficiency, high energy storage capacity, and production of high quality heat as a side effect of the redox reactions. And the singular cell in such fuel cell consists of two porous electrodes, anode and cathode, situated on both sides of the solid electrolyte from each stabilized zirconia. And taking into account the fact that such singular cell is characterized with too low power output, they have to be grouped into bigger units, so-called stacks, where singular cells are separated using so-called interconnects in the form of bipolar flat panels equipped with channels for the flow of the gaseous reagents. And due to the important roles of interconnects shown on the left side, materials for their production, for example, heat resistance, ferritic stainless, Crawford 22 APU steel, has to meet a number of rigorous requirements, from which the most important ones concern electrical conductivity and high corrosion resistance in aggressive working atmosphere. And this aggressive, let's say, working atmosphere, so high temperature, around 800 Celsius degrees, and also oxidizing reductive gases, cause too fast growth of the protective chromium layer on the top, loss of its adhesion, and then further degradation of the material, along with deterioration of the electrical properties. In the end, material undergoes a high temperature corrosion phenomenon, and which leads to the decrease in the efficiency of the whole fuel cell system. So one way to solve this problem is to apply protective conducting layers where the coating materials are evaluated taking into account the following criteria. So high electrical conductivity, chromium migration inhibition and oxidation rate reduction, and simplicity of deposition. And all of the listed materials were investigated till now as the coating materials. So for example, based on rare earth oxides, semiconductors with the perovskites or spindle structure. However, at least one of those requirements was not met. That is why in my work, I proposed alternative coating material in polymer derived ceramics. And these are a very interesting group of materials which draw an attention of scientists at least 50 years ago due to a number of interesting properties. But what is the most important is the fact that we can tailor the material's properties newly on each level of the material's formation. So first of all, we can choose appropriate polymeric precursors containing, let's say, different functional groups and also different amount and different type of carbon. Then we can obtain those materials through different synthesis routes. So the most common is gel, but also we can apply plasma-enhanced chemical vapor deposition, spark plasma sintering, and so on. And also very important fact that we can shape those materials in the form of coatings, fibers, bulk, or porous. And in the end, we can apply a wide range of thermal treatment parameters within shaping, cross-linking, pyrolysis, and crystallization stages. So what are those black silicon aluminum oxycarbide glasses? So these are polymer-derived ceramic materials from quaternary silicon aluminum oxycarbide system of amorphous silica structure. And apart from the fact that they are amorphous, sometimes they are called heterogeneous. Why? Because of the dual form of the carbon inside. So first of all, we can distinguish a structural carbon in the form of silicon-carbon strong covalent bonds, which leads to the strengthening of the glass network and which finally leads to high thermomechanical stability up to 1200 Celsius degrees, heat and creep resistance, and low chemical reactivity. However, on the other hand, when the structure of glass, so let's say some kind of threshold of the carbon concentration in the structure is too high, is exceeded, then so-called free carbon phase is formed, sometimes called segregated or secondary carbon, in the form of highly disordered turbostratic carbon, which induce the high electrical conductivity, piezoresistivity, and scratch resistance when we apply coatings. So, numerous information concerning the positive influence of cationic substitution on the properties of polymer-derived ceramics can be found in the literature. And in my work, I'm concentrated on using the aluminum cations because they introduce more flexible structure and increased thermomechanical stability even up to 1500 Celsius degrees because of the suppression of a carbothermic reduction process. So the aims of my work was to optimize the formation of coatings and to optimize the substrate preparation and withdrawal speed during the deep coating technique, and then to perform anti-corrosive tests in both isothermal and cycling oxidation conditions for both coated and as-received specimens, and also to execute structural and microstructural characterization of coatings after pyrolysis and oxidation tests. So first of all, how everything was performed. So the coating material, I obtained it by means of zoogel method, where in the first step, hydrolysis in acidic atmosphere, I mix appropriate organosilicon precursors, so-called alkoxysilans, with water, ethanol, and after such procedure, after synthesis, such yellowish zoll was synthesized, which was then used to deposit very thin layers on prepared substrate using deep coating technique. And such layers were then dried, so to let the solvent evaporate and the polycondensation occur. And after that, I pyrolyzed samples in inert argon atmosphere at 800 Celsius degrees. And afterwards, such obtained coatings were evaluated, taking into account the performance characteristics, so corrosion tests, and also structure using diffractive analysis and spectroscopic methods, and also microstructure studies using microscopic techniques, along with energy dispersive spectroscopy. So, first of all, in order to confirm the formation of appropriate coating material, infrared spectroscopy studies were performed for bulk material, because plenty of studies for the coatings in the infrared spectroscopy show that there is a really huge measurement error, deviation in the results, and that is why alongside the coatings, we also form the material in the bulk form for these structural studies. So here, the graph presents the convoluted spectra, this infrared spectra, for both undoped and doped material with aluminum cations, and the most important information is the presence of band in both spectra coming from the stretching vibration of silicon-carbon bond, which proves the formation of black glasses. And in case of aluminum modified material, we see bands coming from vibrations of linkages of silicon-oxygen-aluminum linkages, which gives us the first sign of successful introduction of aluminum into the structure of glasses. And then we see the optimization of deep coating parameters via the microstructure studies. And here are showed the cross-section images of all optimized coatings, and we see that the best tightness without any cracks was obtained for the lowest possible withdrawal speed, equal to 5 centimeters per minute. And as you can see, slightly thicker coatings could be observed on a ground substrate, and it is highly probable that it is due to the better adhesion to more rough surface. And also, one more interesting feature can be observed, so the presence of an inner layer independently on used preparation of the substrate preparation technique or removable speed. Around 200 nanometers of such inner layer was formed already after pyrolysis. And this layer was investigated using very interesting study. So the Raman profile death, when we focus the Raman laser firstly on the top, which is represented by a 0 on the right side, and then we go 0.3 micrometers deep down. So we focus the Raman laser deeper into the material. So in the end, the sample is intact. We don't have to cut it, but we can just only put the sample and measure it. So as you can see, around 2 micrometers deep down, we see an increasing intensity in the characteristic band coming from spinel, which confirmed finally that such an inner layer is composed of manganese chromium protective spinel. And apart from that, we can conclude the ongoing amorphization of the so-called free carbon phase based on the shift of so-called D and G band visible on the right side of the spectra. So right now I would like to go to this oxidation test, firstly in isothermal conditions. So here I present an oxidation kinetics which present very promising results. Please have a look at these four kinetics. So the black one represents a pure steel, the blue one represents the first trial with different deposition parameters, and these results are, let's say, comparable, so there was no improvement. However, after optimization of the parameters for silicon oxycarbide coating, 2 years ago we published a paper when we proved that the value of parabolic rate constant was at least 2 times lower. And in case of the aluminum doped material, here you could see that after 500 hours of oxidation, we have at least 1.5 orders of magnitude lower value of Kp in comparison to the pure steel, which means above 20 times lower mass gain in comparison to the pure steel. So such promising results were then confirmed using structural studies. So first of all, grazing incidence, X-ray diffraction. So please have a look first of all from the bottom at the coating. So these peaks, apart from the substrate, come from manganese chromium spinel, as I said before, and then we have a result after 500 hours for our best material. And apart from the usual peaks coming from chromia and spinel, we have some additional reflections which is highly probable come from the hematite, so the iron 3 oxide. And it was confirmed using Raman spectroscopy once again due to the numerous bands coming from this phase, apart from the chromia and manganese chromium spinel. And here I would like to put an emphasis on the fact that the Raman spectroscopy is a really interesting technique which is underestimated when it comes to the corrosion tests. So here I present such a Raman, so-called Raman confocal imaging, and which presents a Raman distribution images on a basis of integrated intensity of Raman bands. So here we see a distribution in this near surface area of amorphous carbon, spinel, chromia, and hematite. So the presence of a hematite, let's say, means that our coating is, let's say, probably acted as a solid barrier against inward oxygen diffusion, because hematite is usually formed in this system when we have a really low oxygen partial pressure. And the distribution of amorphous carbon may allow us to think that some kind of percolation paths were created, which should provide good electrical conductivity in planned tests for the electrical conductivity. And we should move on to the microstructure studies and the comparison of a cross-section after oxidation. On the left side, we see an uncoated material and very thick scale, around 3.2 micrometers. And on the right side, we see our best material and over 4 times thinner scale, which was covered with specially protective nickel layer. And right now, the confirmation we can see with using the EDS mapping analysis. So independently on the thickness of the coatings, on the left around 2 microns, on the right around 1 micron, and after 100 hours of oxidation on the left and 500 oxidation on the right. So independently on those conditions, the thickness of the inner scale which is formed is maximum 700 nanometers, which was then also confirmed using EDS mapping analysis. So what about the cycling oxidation conditions? So we perform 500 cycles for 1 hour with 45-minute breaks. And I would like to add one more thing, because previously I talked a lot about this inner layer of manganese chromium spinel, which is also, let's say, protective. And in this case, I assumed that an, let's say, slightly longer pyrolysis process and slower cooling rate, so not 5 Celsius per minute, but 1 Celsius per minute, should not only provide with lower thermal stresses, but also should induce the formation of a thicker inner layer during the pyrolysis process. And Raman spectroscopy results helped me once again to show that I was right. So the characteristic band coming from manganese chromium spinel is much more intense than DNG bands, conversely to the sample cooled faster. And also, apart from that, on this blue spectrum, you could see a band coming from chromia. So not only let's say we produce a thicker, let's say slightly thicker inner layer, but also it was composed of a spinel and chromia phase. So here I present a microstructure of the surface of both coatings, which are full, let's say, uncracked, fully tight. And here on the cross-section and also on the EDS mapping analysis, it is a fully confirmation of our assumption. On the left, we see around 150 nanometers of this inner layer, and on the right, we see around 240 nanometers of this inner layer of chromia and spinel phase. So what about the mass changes during the oxidation tests? So please have a look at the netto mass change. So at the picture above, so we see that application of both coatings resulted in a significant improvement in corrosion resistance and at least 10 times lower mass gain in comparison to the uncoated steel. However, if we take into account the spallation mass below, here you could see that slower cooling resulted in really promising results, because a sample cooled as usual had the same spallation mass as an uncoated material. And in case of the our improved sample, here we see nearly no spallation observed. So here I present an images taken by camera after 13 cycles, and one can say that samples in the middle, which is, let's say, cooling faster, looks much better. However, these colors just comes from the interference because of the thinner inner layer. And here you could see images after 100 cycles, and also after 300 cycles, and also at the end after 500 cycles. Also, you could distinguish a very interesting feature, which is some kind of a ring around the sample, and it is probably comes from the gravity force acting during the deep coating technique. So probably that the coating is the thickest at the bottom, let's say at the surroundings of the coating. That is why we see such kind of shiny part of the material. So I also performed a microstructural studies of those samples, and here we see a comparison. So an improvement in the microstructure, in the morphology of the sample, which was cooled slower, because we see no, let's say, bigger precipitates, as in case of the sample which was cooled with 5 Celsius per minute, and these precipitates reflects the grain boundaries of the material, because these are formed during the grain boundary diffusion. And also taking into account the higher resolution, higher magnification, we see the confirmation of the mass changes. So in the middle, we see a spallation, so some kind of cracks and spalled material. And on the right side, we see a homogeneous microstructure of probably the manganese chromium spinel, which was formed on the top of our coating. So to summarize, in case of electrical conductivity, the measurements are ongoing. However, the distribution of the free carbon phase allow us to assume that this percolation paths should imply good electrical conductivity. In case of chromium migration inhibition and oxidation rate reduction, we confirmed the improvement, significant improvement in oxidation resistance due to very low mass gain and parabolic rate constant. And in case of simplicity of deposition, easy chip and fast deep coating technique along with Zolger method allowed to control the process settings and to form tight and well acting coatings. So here I would like to acknowledge the listed group of scientists for their scientific contribution, held a fruitful discussion during the preparation of these studies. And also, I would like to thank for the funds from Polish National Science Center, Polish Ministry of Science and Higher Education, and European Union. Thank you very much for your attention.